So there are a lot of very nice problems in the textbook having to do with Bernoulli's equation and continuity equation. And if you go through several of them, you'll figure it out. Here's a sort of what standout, complicated one, in my opinion. So that you see the figure, you'll recognize it as problem 12-5. And the idea in this question is they want to know, okay, how high does the liquid climb up this tube? So this tube is acting like a pressure gauge. And we know that we have 1 atmosphere outside that tube. And at the bottom, we can call this pressure 1. And we know that pressure 1 is going to be equal to 1 atmosphere plus rho g d. In other words, D is going to be equal to pressure 1 minus 1 atmosphere. Okay, and I say 1 atmosphere because you could plug in 1.015 3 times 10 to the minus 5 there, but it's just a shortcut, divided by rho g. Okay, so once we figure this, we can figure out what that height D is, okay, but we'll need to know what the pressure at the bottom of that tube is. And that's really what this problem is about. Oh, going backwards, 1 second. Wait, way backwards. There. Okay, so in order to figure out this pressure, we're going to need to know the velocity at that point right there. So it's going to be a two equation to a known problem. And we're going to need to figure out what the area is to figure out the velocity, okay? Because if they told us that the velocity 0 was equal to velocity 0, the speed of the water, okay, is 0.1 meter per second, okay, at the opening. And they said that the pressure and the pressure gauge is 50 pascals at the gauge pressure, okay? So P naught is equal to 1 atmosphere plus 50 Pascal. That's what they're telling us. The tube location is 0.1 meters downstream. Assume for this problem that water has 0 viscosity. Okay, so that's it. That's all they gave us. So they gave us these initial conditions over here, the velocity, the pressure, and they called it area naught. We don't know what the area is, okay? We know the area at the output, so we can figure out that velocity, we can call this area 2, okay, or 3, I mean. Yeah, let's call it 2. Okay, velocity 2, off the top of my head, I can tell you if the area is half as much as the initial area, the velocity is going to be double, right? So we know the velocity here, 0.2 meters per second. How did I do that so quickly? Because we know that Q is equal to area naught, velocity naught, which is going to be equal to area 1, velocity 1, which is going to be equal to area 2, velocity 2. Okay, all across through, okay, that's going to be the case. And if the area gets cut in half, the velocity gets doubled. Okay, so that's great. We know that. But we need to know the values over here in this intermediate region. How are we going to figure that out? That's the hard part about this problem, okay? And to do it, I'm going to draw a graph. Okay? The area, this is going to be x, and x starts off at 0, and the area is going to be A naught. That's the area at the beginning of this transition. Then, out here, 0.15 meters, x is over here, on the right side, we know that the area goes to half. A naught over 2. And the area at the funny little tube there is going to be at position 0.1. We can draw a line, and it's going to be right there. And that's going to be the area. So you could either do it graphically, or maybe we actually have to do it mathematically. So how do you do it mathematically? Well, one way to do it is you have to write the equation, right? What's the equation for the area as a function of position? So we have to figure out the slope. Okay, is going to be equal to what? Let me see. The slope is going to be equal to it's going to be area naught over 2 minus area naught over 0.15 minus 0. Okay, it's like 9th grade math. So you plug that in, or you simplify, and we get, let's see, 1/2 minus 1 becomes minus 1/2. It's going to be equal to minus A naught over 0.3, which is, it's not good to have fractions and decimals together. We're going to call this minus 10A naught over 3. That's the slope. So what's going to be the y-intercept? Y-intercept is going to be equal to A naught. That makes sense. Okay, that's the position at x is equal to 0. So then the equation is going to be area as a function of x is going to be equal to minus 10 A naught over 3 times x plus A naught. Ta-da! Next, we say, okay, so at x is equal to 0.1, area, let's call it 1, is going to be equal to what? Let me see, 0.1, that's 1 over 10. The 10s cancel. We get minus A naught over 3 plus A naught is equal to 2A naught over 3. That's the hardest part of the problem. Once we know the area, okay? Once we know the area, we can figure out the velocity, right? So I'm going to do that over here. So we can say that, boy, every time, area naught, velocity naught is equal to area 1, velocity 1. Area naught, 0.1, is going to be equal to 2/3 A naught V1. The A naughts cancel. V1 is going to be equal to 3/2 times 0.1 becomes 3 over 10, 3/10, no, 3 20ths, right, of, that's it, okay? So 0.15 meters per second. Okay, once you have that, so does that make sense? Yes. Okay, as the area gets smaller, okay, the velocity goes up. The initial velocity was 0.1 meters per second. At the very narrowest constriction is 0.2. Right there at the tube, it's 0.15. Okay, makes good sense. So it's 0.15 meters per second. What are you going to do with that? Now we're ready to put that into Bernoulli's equation. I'm going to make some space over here. And we're going to see what we can do. So Bernoulli's equation says that pressure naught plus rho g y naught plus 1/2 rho v naught squared is going to be equal to P1 plus rho g y1 plus 1/2 rho v1 squared. We know that the heights cancel. We're going to get rid of those. P naught was equal to 1 atmosphere plus 50. Okay, plus 1/2. I guess it's water. Velocity naught squared is going to be equal to pressure 1, that's what we're looking for, plus 1/2 water, velocity 2, 0.15 squared. Wow. Okay. We're going to be solving for P1. It's not usual that I keep this 1 atmosphere over here, but I will, okay? We're going to get P1 in terms of 1 atmosphere plus a number, you'll see. So it'll be the gauge pressure in a way, okay? So once I'm going to pull out my calculator and we'll figure out what the answer is. So we get equal to P1 plus, 11.25. And here we've got 1 atmosphere plus 50 plus, okay, let's see, 0.1 squared becomes 1 over 100. 1,000 divided by 100 is 10. 10 divided by 2 is 5. Okay, so we've got 1 atmosphere plus 55 minus 11.25. So pressure 1 is going to be equal to 1 atmosphere, right, plus 55 minus 11.25 becomes 1 atmosphere plus 43.75. Pascal. So it's sort of mixed units, okay? Or the other way we can say is that P1 gauge is equal to 43.75 Pascal. So you plug that in over here for D. Okay, where we do the square one, right? So the atmospheres cancel and we get 43.75 divided by 1,000 divided by 9.8. equal to, this is a long done out problem, divided by 9, 8, 4.46, 4.46 millimeters. That's the answer. That's how high the water. Look, that's the longest problem. That's the hardest problem, I think. Look at that page. Pretty complicated. I hope you followed.